Welcome back to the ProCaaSo trial site series. Today, we're going to delve into the I/O task and learn how it plays a crucial role in the operation of your system within ProCaaSo. This video will teach you to understand the basics and purpose of an I/O task, explore data models and their relationship with state schemas from the system definition, and dive into the setup and functionality of the I/O by adding our environmental sensor to the I/O task. Remember, the software package designed to run your system is known as the ENS, which includes tasks, the I/O and app task, manifest files, and a views folder. Today, our focus will be on exploring the task folder, particularly the I/O task. The I/O task is essentially a Python program that facilitates communication between your hardware and the ProCaaSo event bus. It operates in an infinite loop, pulling the hardware at set intervals, reading and writing data, and interacting with the event bus. This is crucial for real-time data handling and system responsiveness. One key feature of our system is the ability to incorporate multiple I/O and app modules with a single ENS package. This allows for standardizing system control while providing the flexibility to customize and organize hardware and control logic as needed. Let's demonstrate this by adding a second I/O module specifically for our environmental sensor. Here's a quick overview of the I/O task folder that we are going to review today. We will go over the following files: models.py, which stores our data models and corresponds to the state schemas in our system definition; CIP_objects.py, which defines our communication protocol and unique identifiers to communicate with our physical hardware; and logic.py, which stores the user-defined logic that we want the hardware to execute; and lastly, the ens.py file, which is the default entry point to the ProCaaSo framework event bus. Let's open our ENS package in VS Code. You'll see there are two I/O folders. Click into IO2. Before diving into the files, let's discuss what data models are and why they're crucial. Data models in our Python code reflect the structure defined in the system definition state schemas. These schemas allow user interaction with data on the event bus, enabling seamless communication across the different parts of our system, from the app tasks to databases and the ProCaaSo Anywhere UI. Now, let's walk through our models.py file. This file is crucial as it defines the data models that synchronize with the state schemas from our system template, facilitating attribute data communication with our ProCaaSo event bus. For the first part of this file, we'll go over the standard configuration that we recommend to use ProCaaSo. So first, we import all of the necessary libraries for this file. Pydantic is used to enforce data types, ensuring that our data conforms to specified schemas, and typing helps set up a foundation for type hinting, which is crucial for clarity and error reduction in our code. Next, we define a type variable called stateModelType, which is constrained to classes derived from base model. This generic type will be used in defining more specific data structures. Then, we define the fully qualified name class, which ensures each data model's attribute is correctly identified on the event bus by providing a structured way to define where each attribute belongs in the system architecture. Then, we define a combined model class. This class combines a fully qualified name with any data type that we specify. It includes methods to return dictionaries of the fully qualified name and the data, as well as the method to return the type of data. This combined model is essential for tracking data flow through our system. Alright, now let's jump into some follow-along code. Let's define a new class called mState to be a data model for our environmental sensors. Here, we'll specify the default values for temperature and humidity, which again are the same parameters that we define for this sensor in our system definition. Then, we'll go ahead and create a new class called mViewDT for user-defined type to combine both our model and fully qualified name together. Notice that the fully qualified name looks familiar. We use this to tie our Python code to the system definition and to the appropriate components, instruments, and attributes that we want to store our data in. By adhering to the structure, we ensure that all the components in our ProCaaSo environment communicate effectively, maintaining data integrity and consistency across different parts of the application. Now, we will review the CIP objects.py file. This file is crucial for linking each component within our I/O map to its corresponding physical hardware through appropriate parameters and unique identifiers. For ease, this file is already defined for you. But let's explain what this file does. We start by importing the necessary libraries. We import any from the typing module, which enables type hinting and enhances code readability and maintainability. And then we import ProCaaSo from the C3PO library, which allows for Ethernet and IP communications, which is crucial for interfacing with CIP devices. Next, we define the I/O logic class that inherits from ProCaaSo. This setup is essential for a specific CIP device, enabling it to communicate over Ethernet and IP. Then, we define a dictionary of parameters for the device, extending the default parameters from ProCaaSo. Inputs is a new parameter that we're adding with a specific address, which retrieves all values from our mock.io module. The constructor initializes the parent class with a host import specified in the I/O map, and the string method is overridden to provide a meaningful string representation of the device. Next, we have the read values method, which performs a substitution for the inputs parameter and attempts to read the values from the device. If an error occurs, it closes the gateway connection and returns none. And lastly, we have 3 methods to convert the raw sensor values to more meaningful data. We have our raw value to mA, which converts a raw sensor value to milliamps, milliamps to temperature, which converts the milliamps to temperature in Celsius, and lastly, we have the milliamps to humidity, which converts the milliamps to humidity percentage. These methods use established formulas to translate the electrical signals from the sensor into human-readable data. Now, let's go over the env.iologic.py file. This script defines the communication I/O logic for the environmental sensor, utilizing an Ethernet-based connection to interface our MOXA device for reading and writing data to the event bus. We begin by importing essential libraries and modules. Sync Harness Client handles the interaction with the event bus. I/O Logic manages the communication with the hardware as we previously just defined it. Env State and Env UDT are the data models from our models.py file, and Logger is used for logging purposes. Next, we define the environmental sensor logic function. This function encapsulates the logic for interacting with the environmental sensor through the MOXA device. It includes retrieving and updating attribute data from the event bus and managing data flow between the hardware and software. Here, we attempt to retrieve the current state of the environmental sensor from the event bus by using the getAttributeState function to access the temperature and humidity component, thermohygrometer instrument, and state attributes from the system definition, and we set the data from the event bus equal to the data model. We'll go ahead and add in some debug logs to help track the flow and pinpoint issues. Next, we check the Ethernet connection in the MOXA device and attempt to read raw data. If successful, we proceed. Otherwise, we can log an error. Caution: excessive logging can consume resources and potentially cause performance issues and other internal problems. It's wise to be mindful of the volume and verbosity of logs generated to maintain system health and performance. If we are successful in retrieving values in our MOXA, we will convert the raw sensor readings into meaningful data, and lastly, update the environmental state model accordingly. Errors during this process are logged for troubleshooting. Now, we'll explore the ens.py file, which serves as the entry point for the user code execution and the I/O task of ProCaaSo. This file is crucial for initiating the application and managing data communication with the event bus. We begin by importing all necessary modules and libraries. This setup includes runtime operations, our data models, CIP communication objects, and the logic to handle environmental sensor data. Here, we define a startup function decorated with io.startupExpression. This function is executed at the start of the application to fetch and log I/O map data from the event bus. It helps ensure that our system is correctly synchronized with the event bus at launch. We define a dictionary to store I/O map data specifically for the environmental sensor components. This dictionary is populated with the I/O map data retrieved using the getIOMaps method, which fetches the data for the temperature and humidity sensor from our system definition. In this segment, we iterate over the I/O map data stored in mapping dictionary env, and inside the function addInstance, we adjust the io.execution delay to 0.1 seconds. This setting determines how frequently the I/O logic for the sensor will run, ensuring timely updates and responsiveness. Then, we call the envUserLogic function that we defined in the envUserLogic.py file, and pass in the initialized communication object and the client from our framework. Finally, we call the io.start function to initiate the application. This ensures that all configurations and preliminary setups are activated and the system begins processing data as intended. The ens.py file plays a critical role by starting the application and establishing a bridge between our code and the physical hardware through the event bus. It's defined to ensure that the system operates smoothly and data flows correctly from the sensors to the application logic. Join us in the next tutorial where we'll dive into debugging techniques. We'll show you how to ensure your code is performing as expected by using Cindy for remote tunneling. Don't miss it as we equip you with the tools to optimize and troubleshoot your ProCaaSo deployments effectively.